Just a question, how many of you have had any exposure to aeroelasticity at all? Okay, so many of you have not. So I decided, instead of coming here and talking about advanced research and kind of dive right into all the great things that are done, I'm going to do it more in a tutorial kind of a way. Give you some background to a very important, exciting field, and then send you on your way to explore it. So first of all, a very brief tutorial about some essence of aeroelasticity, and I will try to tell you some stories about aeroelasticity along the way. So you look at this impressive machine. This was a World War I era bomber that the British built. It for a time. It was mighty, and it was called the Handley Page 0400. And here you see it, pretty impressive machine, actually so impressive that for many years later on, every big airplane that the British built, they called him a Handley Page, even though it was built by some other companies. And so it turns out that during the service of this airplane, as the pilots were accelerating and reaching a certain speed, the airplane started shaking, and started shaking dramatically. The shaking came from the tail, and it was so bad that the pilots, if you see here a statement for report, which says the experience for the pilot is terrifying. There's a reason why I used red font here for terrifying, because we're going to talk a little later about the psychological issues involving with flutter and aeroelasticity. And so they called a genius of the time by the name of Frederick Lanchester. So how many of you, so you know, I'm going to give you some homework. Go and look at Wikipedia and look at Lanchester. This is an absolute genius and polymath who did everything from designing cars to developing speed regulators for steam engines, to inventing operations research, actually. He is considered one of the two creators of operations research, and also writing the first books on aeronautics, inventing vortex theory. Remember flight dynamics? How many of you took a class in flight dynamics? How many of you know what the phugoid is? So he created this term, actually. So this is absolutely, so they call him. And he looked at this, and he writes the first report called Torsion and Vibration of Tail of an Airplane, and the British follow through with this one. And he basically discovers that what happens is you see these elevators here. They are not connected to each other. So as the tail gets pushed up, the elevators, because their CG is in the back, the elevators kind of get to lag, and so they develop an angle of attack, which creates lift. And the lift then accelerates the motion. It pushes it in this direction. That pushes against the elastic resistance of the airplane until it stopped, and then it would reverse it. But that time, the tail goes down, but the elevator, because of the inertia, wants to go up. And so you have the opposite effect. Now the elevator goes up, now the aerodynamic force turns around, and the airplane shakes. This is the first reported incident of what we call flutter, or flutter instability, that interaction between structural dynamics and aerodynamics in a dynamic way on an airplane. So in order to describe the structural dynamics of an airplane, we usually take the very sophisticated, this is a B-2 bomber, and you can see a very sophisticated mathematical model of the B-2 bomber. We usually don't use for aeroelasticity the very detailed finite element model. We look at the essential motions. And so we use a set of shapes of motion. Here you can see some of the low-order mode shapes. So I would assume that all of you know what mode shapes and natural frequencies of structures are. These are the shapes at which the structure would oscillate if left on their own without damping. So basically, you say, in order to understand what this is doing, let's describe the motion as superposition of these shapes. These then will serve as what we call generalized coordinates. And if I know how much each generalized, so here is the motion, so it's generalized coordinate number one, it's some shape times how it will change with time, another shape, how it will change in time. So these are the generalized coordinates, generalized displacements. And by this superposition, if I know these generalized displacements, I know what this airplane is doing, so I'm going to work with a set of mode shapes and natural frequencies. Each one of them has its shape, each one has its natural frequency. So the equations of motion for a structure that is linear, that is limited to small perturbations, there will be, and this is Laplace transformed, there will be some inertia matrix, there are going to be some damping matrix, there are going to be some stiffness matrix, that's the structural part. And since the whole thing is moving, and since aerodynamic forces depend on shape and motion, then on the right-hand side, you will have an aerodynamic matrix. This is for what I would call self-induced aerodynamic forces. They depend on the motion, and then there are going to be forces that are aerodynamic due to gusts, and there are going to be some external forces. So here you can see the inertia terms, the damping terms, and the stiffness are coming from the structure. And you see the aerodynamic terms moving to the left-hand side and basically modifying the dynamic of the structure. And on the right, you can see the excitation coming from gust and from external forces. So in a way, you can view it as a kind of a feedback mechanism of nature. Here is the structure. The structure is a system that if you apply force to it, it would respond by some motion. And the motion will be a combination of rigid body motion, the whole thing is moving up and down, and the formation. But if you have aerodynamic forces, the aerodynamic forces are dependent on the motion and the formation, and the aerodynamic forces then will feed back, and they would modify the forces acting on the structure. So you have a kind of a natural feedback loop. And indeed, since the British did pioneering work on aeroelasticity, and some of the greatest contributions were done in the 20s and the 30s by the British, it was natural for the British person, this is a famous professor of aeroelasticity, A.R. Collard, who in 1946 suggested what we call the Collard triangle, saying aeroelasticity is about the interaction between elastic elements, inertia elements, and aerodynamic elements, and all these lines describe different phenomena associated with these interactions. Taking these equations and putting them in state space form, the form in which controls people like to work with, and again, limiting ourselves here to linear systems, the equations will be what you'll see here in the bottom. So there are going to be some vector of states, which will include the displacements, the velocities, some of the aerodynamic behavior, and so on. And so you will have the rates of change, a matrix times the states, then going to be another matrix from the inputs, and then going to be some outputs that you measure. In general, this A matrix and B matrix and C matrix can be dependent on the states. They can be dependent on outside parameters like what Mach number you fly, what you do with the airplane, and they can be dependent on time. But we are going to limit ourselves here for the simplest case, which is constant coefficients. And so I hope you all remember from your basic controls class that the stability of a system like this depends on the eigenvalues of this matrix A. They are also called poles. And in general, they will come in complex form. And so they can be either complex and they will come as complex conjugates, or they can be real. And the stability of the system will be determined by the real part of these poles. So when you can see here, you can see the real part and you can see the imaginary part. You can see when the real part is positive and the imaginary part are finite, you have a diverging oscillation. When the real part is negative and the imaginary part is positive, you will have a converging oscillation. If the real part is positive, if the real part is the pole, basically, if the pole is real, and it is on the real axis here, you have a divergent exponential motion, and if the pole is real but negative, you will have a convergent motions at the exponential. And if the pole is purely imaginary, then you have simple harmonic motions that does not decay. So basically, when you look at the mathematical model of a dynamic system, you look at the poles, you look at the eigenvalues, and you look at the real parts, And then, depending on these impulse, you know if the system is stable or not. You can have all the eigenvalues, all the poles, you can have them stable with negative real parts. It's enough that one of them will have a positive real stuff and the system will go unstable because there's going to be an oscillation of this part. And the limit between the unstable and the stable when the system behaves in purely harmonic motion is what we call flutter. So flutter usually, when you look at the language, is that crossover between unstable and stable. But in colloquial English, when you say flutter, you mean the whole behavior. Once the system goes unstable, we will also call it flutter. Now, just to give you a taste, I plotted some nice figures, but usually it's kind of dirty and complicated. This is a Boeing plot of a 737, and you can see how many eigenvalues you have to track, how many poles you have to track, and you can see how they change when you increase the speed. So sure enough, when there is no speed, everything is stable. There is no aerodynamic forces. But as you increase the speed, at some point, some of these poles will become unstable, and then the system will, of course, diverge. So it's a huge challenge when you analyze, when you optimize, and when you design controllers to deal with systems which have so many poles, which have such a high order. When you look at the way that the system becomes unstable as you increase the speed, it's always a branch, it's always a pole that where you increase the speed will cross from stable to unstable. The question is how it will going to cross. On the left is what we call violent flutter. The reason is, this is the damping in a pole. The reason is that very close to the flutter speed, you still have a lot of damping in the system. So just imagine a flight test or wind tunnel test. You increase the speed and you check, and you increase the speed and you check. And you're very close to the flutter speed and you check, and the system is very well damped. And then you push the speed a little bit, just a little bit, and you are already very, very unstable. And within a fraction of a second, the system will disintegrate, and I'll show you a movie to get you a feel of what we call violent flutter. Moderate flutter is, as you increase the speed, you begin to see the decrease in damping way before it actually becomes unstable. So when you do the testing, you can do some kind of an extrapolation. You feel that the system is approaching an instability, and that's a much easier thing to deal with when you do flight tests and when on the line is the safety of the airplane. And then you have these things, so this is what we'll call moderate. Then you have this mild or shallow, where way before the flutter speed, the damping is already low. The system is already shaking a lot because the damping is low, but you can still push the speed higher and higher and higher way before you will become unstable. And even when you become unstable, even when you crossed this and you are unstable, the rate of divergence is going to be slow. It will take some time until the motion will build up. And so the pilots will have enough time to slow down. And this is stuff that I'm telling you not only to give you a basic education about aeroelasticity, but because it has importance in the issues that we're going to discuss, which is active flutter suppression. How to apply control, active control to a system like that. The question of whether you are controlling a violent mechanism or a mild mechanism or a shallow mechanism has enormous significance. Since no system in real life is really purely linear, there are always some nonlinearities. You can encounter in aeroelasticity the same thing. I'm not going to talk much about nonlinearities in structures. This is a fascinating area. Nonlinear with systems can behave in crazy ways, and they're not easy to deal with. But one particular, just to give you a taste of what can happen with one particular nonlinear, just imagine a system where as you push it more and more and more, you face more resistance. For instance, just imagine if an airplane wing is oscillating with larger and larger oscillations, the damping of the system, just because of the grinding of parts, becomes higher. Or that it begins to hit against some structural resistance and becomes stiffer. So what can happen is, if you look at a mechanism that like this, let's say that now I fly more than the flutter speed. So if I fly more than the flutter speed, the system is unstable, and the airplane wings and the parts begin to oscillate. But as they oscillate at larger and larger amplitudes, they see more and more stiffness. You see the force deformation, you see the steeper slope here means that the system resists it more. And so what will happen is something like this. It begins with an instability, the amplitude will build up, but the amplitude building up is against the stiffening of the structure, so at some point a balance would be reached, some equilibrium will be reached, and the system will not diverge completely, it will keep oscillating with a limited amplitude, and this is a typical example of what we call a limit cycle oscillation. And again, it's interesting to know about it, but it will have relevance to some of the stories that I'm going to tell you a little later. So then how do we define Flutter? We have to agree on the term. We can define it as the destructive linear Flutter, where if you cross the Flutter speed, the system will disintegrate. But what about limit cycle oscillation? Is this Flutter or not? The system will begin with some divergence and then it stays at some amplitude. So is this Flutter? Is this limit cycle oscillations or what? So we can argue about this. What we'll go to the British and we go to a beautiful book that was written by Fraser, Duncan and Kohler, the great British engineers who basically led the way in aeroelasticity and structural dynamics, published in 1938. And here is how they define it. They say, in the practical sense, Flutter means an oscillation which grows, and finally either breaks the structure or remains bounded at some amplitude whose value is dependent upon the departure from linear laws, and so on and so forth. So it's an aerodynamic structural oscillation. It's an aerodynamic structure that can either go unbound or stay bounded, but it has to have an aerodynamic structure. So we talked about stability. What about a stable system? So we have a stable airplane. It doesn't flutter. You push on it, it will oscillate and decay. You hit it, it will oscillate and decay. Now, when you fly, you are subject to disturbances all the time. You're like a boat on a wavy lake. You're an airplane in a gusty sky. So the airplane is shaken by gusts all the time. And so here are the equations of motion now in the frequency domain, where the Laplace variables become j omega. Here is our airplane flying into an area of gusts. And so we can solve here, we can solve for the response of the airplane. The airplane is not going to break, it's going to shake. It's going to shake a lot, but it's not going to break because of instability going on its own. And so by looking at this, and by looking at how much response I get at different frequencies, I can have a lot of insight about what the structure is doing. So as you know, again, dynamic systems of this kind have their natural frequencies. In airplanes, the structure is lightly damped. So when you subject it to a spectrum of inputs, whether you do it by slowly varying the input, increasing the frequency, or by subjecting to a random field, which basically hits it with all the frequencies, they serve as kind of filters. And they respond more around those frequencies, natural frequencies, where they have low damping. So this is I think this was a B-52. Yes, this is a B-52 flying into turbulence. And you see, these are power spectra. So this is a measure of looking at the frequency content of a random signal. And you can see that the airplane basically filters the input and responds mainly around its natural frequencies. But flying them, you can see where those natural frequencies are. And they can behave almost as if, even though they are subject to random inputs, they can behave always as if they oscillate in some combination of sines and cosines. So here we can see some beating phenomena where you have oscillation in two frequencies that are close to one another. Again, all this seems to you just an introduction to elasticity in general, but it's going to lead to what I want to talk about, which is active flutter suppression. Here are two examples. This is a Lightning fighter jet. Again, go to Wikipedia. Those of you who love airplanes, this is a cool airplane for you to know. I built a model of this when I was a boy. At the time, it was the best performing fighter jet in the world, and it's just a fantastic airplane. And this is a British Trident 3-engine passenger jet. And what I want to show you is also look at the natural frequencies. Here is the fighter jet. So it responds, the first frequency is the rigid body short period of the airplane, where the airplane is responding as a rigid body. And you can see it's about, I don't know, 0.6 or 0.7 hertz. And the next one will be a frequency where most of the conversion of the wing bending, and that's going to be around 8 or 9 hertz. And look at the passenger jet, and this is a jet with a clean wing, so the engines are in the back. So you can see the short period is about maybe 0.3 hertz, and the first bending is about 3 hertz. But actually, for passenger airplanes today, with their engines on the wing and with a very high aspect ratio, the bending frequencies of the wing go down, and you can have first bending at 1 hertz or 0.8 hertz. The point is that the bending, the elastic frequencies and the elastic motion begins to be really close to the rigid body motion. And if in the past you want to design a control systems that would control the rigid body motion of the airplane well, neglecting the flexibility, now you can't do it anymore because everything is so close and so coupled. And so this brings us to a particular type of flutter, which is called body freedom flutter. It's just the names that we use, in which the instability is actually not an interaction of some elastic modes, but an interaction of an elastic mode and a rigid body mode. And it's usually an interaction between the short period rigid body pitching of an airplane and some form of bending of the airplane. You can see here a Lockheed Martin sensorcraft, and very high aspect ratio, very flexible wing. So sure enough, the bending frequency of the wing is very low. It also is very short. So its rigid body pitch moment of inertia is very small, so its short period frequency is very high. And when you look at the root locus here, you can see that as you increase the speed, the short period frequency goes up, and the root bend and the wing bending goes down. The frequency becomes really close. You get some strong interaction between them, and one of them goes unstable. And so what will happen, the airplane will lose stability in a flutter. It's really flutter, but the flutter involves a mix of rigid body and elastic motion called body freedom flutter. Here are airplanes that had this. This is a General Dynamics RB-57. This is a Canberra kind of a airplane. It's very high altitude, huge wing. This suffered severe body freedom flutter. By miracles, they did not lose an airplane at high altitudes. This is the X-29 forward swept wing. So again, those of you interested, I'm going to cause some, I hope I'm going to cause my colleagues some trouble by all of you flooding to the aeroelasticity class, because this is really a cool subject, and I think you should all, you can't be aeronautical engineers without knowing aeroelasticity. You just, if you love airplanes, you have to do it. So make them life a little hard and flood their classes and take them seriously. Carlos is going to kill me. So forward swept wings have this tendency, as the speed goes up, the natural frequencies go down. And so on an airplane like this, as you fly faster and faster and faster, the first bending frequency of the wing goes down, and it begins to couple with the short period rigid body motion, and you can get this body freedom flutter. And flying wings, this is Lockheed Skunk Works test wing, where you can see body freedom flutter. So when you deal with some unusual configurations, which are very compact and very short, but with very long and flexible wing, you will get this kind of instability. So what I want to do now is, now that we talked about these basic concepts, I want to show you a very short 2-minute video which will give you a taste of each of them, and then we will move on. Because it's important for you to really have some feel for it, not just listen to the theory, but have some feel for it now. So how do I do this? Okay, so now you'll see a few examples of violent flutter. Remember violent flutter? It happens very quickly and, okay, and this is it. Now you'll see a case of moderate flutter. It goes unstable, but when you approach it, you see a larger and larger motion, and it takes time. This is from the transonic dynamic tunnel at NASA Langley. This is our wind tunnel. This is a very simple wing. It has moderate flutter. As you approach it, it moves, but and then it's pretty scary. And now you'll see a few cases of maybe mild flutter, maybe limit cyclation, again in our wind tunnel, historic Boeing. So you see also that flutter, what we call flutter mechanisms, the airplane can go unstable in different shapes, different ways. This is what's called an anti-symmetric motion. You see that you have a lot of bending motion. This is probably a B-52. This is symmetric. You better take care of this in design, right? You don't want to fly an airplane like this. And I think next you will see an example of body freedom flutter on a passenger, on a bomber, on a typical swept wing, also taken in our wind tunnel, somewhere probably in the 50s or the 60s. So see how the airplane is pitching up and down as a rigid body and the wings bending up and down. So you have this body freedom problem of coupling between the rigid body motions of the airplane and the elastic motion of the wing. So this is all in our wind tunnel done maybe when I was born, I'm not sure. Okay, we got the idea. So, of course, when you design an airplane, you have to make sure that this never happens. And how is this? How is it? So in an academic world, usually you focus on research. You don't worry about certification. But you have to remember that everything that you do has to be certified. It has to pass some rules and regulations to make sure that it is safety. In the aeronautics industry developed over 100 years or so a set of safety factors and design processes that would guide what can be certified or not. It's not enough to design a great airplane. You have to show that you met many, many requirements. For instance, in the static case, you look at all the possible loads that can be applied. You look at all the maneuvers, all the possible flight conditions, the worst cases, all the possible loadings of an airplane, full fuel, half fuel, passengers standing in line for the bathroom in the back, passengers in the front. You look at tens of thousands of cases. For each case, you calculate the loads, and you have to show that under the most critical loads that the airplane can ever see, the structure is safe. And then you apply a 50% safety factor to this, where you allow basically failure of the structure at 50% more than the worst case loads that you will see. So this is what we say limit load and ultimate load. How did this come about? So I dug out into the history and I found this very interesting article by Shanley, who used to be a professor at UCLA, about, honestly, how they came up with this factor. But this factor is still with us today. So every airplane that the FAA certifies has to meet this factor. You have to show that the worst case scenario is covered and that the airplane would not fail at 50%. What did I do? When it comes to flutter or gust, the FAA requires that you work within what we call a VN diagram. How many of you have seen it in your airplane design courses? So what you see here, you see speeds and you see load factors, which basically the accelerations of the maneuvering airplane. And I'm not going to talk much about it, but this will cover all the possible maneuvers as combination of speed and pulling up acceleration. For us right here, so there are different speeds. There is VA, which is the maximum speed of the maximum maneuver allowed. There's going to be V cruise, which is the speed at which the maximum gust loads would be applied. And there is VD, which is called design dive speed. This is the highest speed that an airplane can ever see. And the requirement of flutter is that you have to show that your airplane is free of flutter up to 15% more than design flight speed. It used to be 20%, but a few years ago, with more confidence in the tools, it was reduced to 15%. So the requirement says, here is the speed versus Mach number. It says for each altitude, depending on the speed of sound, you have a line. So this is the line of highest altitude, this is the line of lowest altitude, at each altitude, what is the maximum Mach number? What is the maximum design? So this is design Mach number, design speed, that the airplane will ever see, and then apply a 15% margin of safety. and show me that there is no flutter before that, there can be flutter exactly there. So if you show me that the airplane gets flutter at 15% above design speed, that's fine, but I'm not going to allow you for this to be too close to the actual design speed. So at design speed, you have to show me that you have damping of a level that is at least 3% damping. So when you look at the damping coefficient, structural damping coefficient, you have to show that at design speed you have at least 3% damping, and then flutter at 15% more. So I promise I tell you stories. I told you about the Handley page. I showed you a few videos that I hope you remember. And rest assured, by the way, is that the airplanes that you are flying, even when they shake like hell in turbulence, even when you pray to God because you think the airplane is going to, you land in Seattle in the winter, and the airplane is swaying and shaking, they are not going to flutter. They are well designed for flutter. Here is a story. This is a fighter jet. This was actually, I think, the first operational supersonic jet that the United States built. And this is the time of the Korean War in the 50s, and this is the Super Sabre, the F-100. So in the F-100, it's very interesting. In order to allow it, it flew Mach 2, so it was the first operational Mach 2 airplane. In order to do this, again, those of you who love airplanes and know, you have to have very thin wings because you have to reduce what we call shock-induced or wave drag. And so the wings have to be very, very thin, so they have to be very, very flexible. So they had to redesign the tail. And the way they did it, you have an all-movable tail, so the two tails move together. There is an actuator buried somewhere here. The moment arm of the actuator goes below the exhaust here, lo and behold, and there is a hydraulic actuator that pushes these back and forth. Well, if you take off and you want to reach 40,000 feet very quickly, then you use your afterburner. You use the afterburner, this area becomes hot. This area becomes hot, the hydraulic fluid in the servo actuators becomes hot. And so the actuator stiffness goes down. So they lost horizontal tails to flutter 7 times. And by only miracle, they always lost only one of them. So just imagine today, this will go to Wall Street, this will be in the news, this will lead to the CEO of the corporation to basically be fired on the spot. Just remember sending an airplane again and again and again, and 7 times losing the tails until they figured out what to do. In addition to the interesting story here, the message is that flutter behavior is extremely sensitive to changes in the parameters of the system. A hot day, a cold day, a little damage here, a little damage there, things like that can completely change the flutter behavior. And so when you certify an airplane for flutter, you have to make sure that you covered all your bases, that you have not neglected even one possible change. There's another story. This is an Airbus A310 operated by Air Transat, a Canadian company. It took away in 2005 from Cuba on the way to Quebec. Somewhere along the way, the pilots felt something was strange. They didn't know what was going on, but the airplane didn't feel right. They felt something was awfully wrong. They managed to turn around and land back. They look at the tail. They lost the rudder. So why did they lose the rudder? It was built by composite technology where somebody didn't pay attention, and the way it was built did not protect it completely from moisture, so it absorbed moisture, and over cold, hot, and so on and so forth, it froze, it expanded, froze and expanded, and so slowly, the stiffness of the rudder and the stiffness of the connections to the rudders were deteriorated, and they lost the rudders in flight. So things like that can get you into trouble if you don't take care of it a priori. So this is just very quick to show you, this is from the certificate, the regulations. So the FAA, in order to certify an airplane, you have to be half an engineer, half a lawyer. You have to, I mean, you're laughing, but if you go into the world and you think for 1 minute that it's all about mathematics and all about testing, forget it. It's about government regulations, it's about insurance rates, it's a lot of lawyerly kind of stuff, and you need to know, of course, medications, things like that. So this is from the FAA regulations that you have. It shows you how you have to cover every possible nominal configuration and condition. You also have to cover every possible damage, and you have to show the FAA that you did that, otherwise it wouldn't certify your airplane. So if Flutter behavior is the result of a physical feedback mechanism where aerodynamic forces feedback, then why not use active control and add another feedback loop? Why not measure what the airplane is doing, sense it through some accelerometer, strain gauges, whatever, have some controls computer that using some control laws will then drive actuators, and these actuators will also modify the motion of the structure. So in our case, in the simplest case, just let actuators operate control surfaces. Going to be the tail surfaces, are going to be flaps. And so if the airplane is shaking too much, or if the airplane is approaching instability, let the control law stabilize it. Let the control surfaces shake in a way that would stabilize the system, and this is what we will call active control. So the idea has been around for a long time, but people were afraid of it. The fear was also, what if something happens to the control system? An actuator gets stuck, the computer doesn't work, so what's going to happen? So some work on this was done in the 50s and the 60s, but nobody dared putting it on an airplane until the YF-16. This was the competition of the early 70s for the United States lightweight fighter. The YF-16 competed against the YF-17. And one of the innovations of the YF-16 was it was a relaxed static stability airplane. This is assuming, forgetting that it is flexible. And it is flexible, by the way. This is an airplane I spent a lot of my life on, and when you see an F-16 on a line in some exhibit, go and push on the wing, and you will see that you can bend the wing with your hand. It is so thin, and it is so flexible. Just rigid body, they allowed the airplane to be unstable in order to gain some performance benefits. And so by that time, some things happened. The actuators available became faster. In the past, you couldn't do it. Actuation was cables and rods. They just didn't have enough speed. Now you have hydraulic actuators that were very capable, so you can deal with phenomena at high frequencies. Computing became more powerful, so you can have a computer here that will be fast enough, controllers that are more established. So control hardware improved, the mass modeling improved, the control law synthesis matured, and now you have better ways of designing controllers. And the push for effective airplanes was unrelating. So this is the airplanes that saw for the first time relaxed static stability airplane. And so this is from a B-2 bomber. So you can see that if you want your airplane that is unstable to depend on an active system to stabilize it, you have to make sure that under no circumstances this system would fail. So you go with systems which have multiple redundancies. For instance, this is a B2, and it has it has 24 actuators. It's quad redundant. It means it has 4 independent systems where the system can function on only one of them. So you can use 3 systems and still the airplane will be operational, which means the hydraulic lines, the servo actuators, the controls computers, the control hardware, everything has to be quadruple redundant in order to make sure that whatever happens, the system would never lose a code because of. So as control and the control aspect began to be more and more important, now was an opportunity to look at what it would take to apply it not only to statically unstable airplane, which is mainly rigid body, but to flexible airplane. And maybe we can use active control to fight against Flutter. And so in 1997, actually, but then in 1999, Peretz Friedman wrote a very nice paper, which was an overview of aeroelasticity. And so he took the collar triangle, remember the collar triangle, elastic aerodynamic inertia, and he added, there was a thermal effect here, which is very important when structures get hot and the stiffness of the structure becomes important as function of temperature, and then the control here. So now we have this kind of a hexadron which captures all the possible interactions, including active control. As I said, the idea was around for a long time. And I can show you, as I show you here, papers that go to the early 50s, which talk about the possibility, but the technology was not there. Actuators were not fast enough, controller was not good enough. It's only in the mid-70s, towards the end 70s, that it could apply to rigid airplanes, and only in the 80s and the 90s where you could apply it to flexible airplanes. This is from the classical book on aeroelasticity by Bishop, Ashley, and Huffman, published in 1955. And they say, in the introduction to the chapter on Flutter, they say, there exists an excellent possibility of improving Flutter performance by somehow installing in the structure a properly designed, rapidly responding automatic control system, actuated in closed-loop fashion by the motion of the to be stabilized. However, we cannot count on the human pilot to compensate for Flutter because it's too fast, and the human pilot cannot compensate for this. One of the things that, in addition to the development of technology, one of the things that triggered more interest in active Flutter suppression was the saga of the American SST. Most of you were not even born. In the late 60s and the early 70s, the United States worked on a SST, supersonic transport, in competition with Concorde. It failed. It failed miserably, and it was stopped, basically. And at that time, it was stopped, I think, in 71. That almost led to Boeing going bankrupt, because Boeing was the center of activity on this. And one of the reasons that led to the failure of the American SST was a Flutter problem. It's a very flexible, long airplane, like a flying needle. And the methods of the time were not good enough in order to develop a design that would be good for Flutter and it would be lightweight. In airplanes, in general, weight is a critical issue, let alone supersonic airplane, where every gram is important. Actually, here you can see that the only way they could solve the Flutter problem by adding something like 10,000 pounds for the airplane, completely killed the project. There were other reasons why the project was killed. But you can see then that drove a lot of interest in active Flutter suppression, because if I can solve the Flutter problem by active controls, by using the control system to move the control surfaces to eliminate the problem, I would save all this weight and I would make the design possible. So active Flutter suppression then can be viewed in two ways. One way, you can view it as a way to fix things. So after you design an airplane and you discover a Flutter problem and you can't find a way to solve a Flutter problem, then you use active controls to fix it. And this is the case of the F-18, and this is the case of the Boeing 747-8, and this is the case of any Air Force operating fighter jets, because each fighter jet, you designed the F-16 in 1974-75, still new missiles, new bombs, new electronic pods. Each configuration like this is a different Flutter story. You have to deal with tens of thousands of configurations. Fuel tanks, yes, no. Missiles, yes, no. One missile, two missiles, this bomb, that bomb. Every configuration is a different dynamic system, different natural frequencies, different Flutter mechanisms. How do you design an airplane that will be okay for things that are going to be built 25 years later? So if you could use an active system to deal with it, that would solve your problems, you make your life easier. So remember this statement, this is another story. Remember this statement about the human pilot not being able to do active Flutter suppression. So in 1984, two crazy people, actually, and their genius relative flew for the first time an airplane around the world non-stop. It was called Voyager. And if you have some time, I really recommend that you, again, go to WikiLeaks and look at Voyager, but not the Voyagers that went to Mars, because there were ones that went to Mars, but Voyager airplane. They flew in 86 for 9 days at about 160 miles per hour. The airplane was a marvel of design, extremely flexible. You can see it taking off. Actually, when this is taking off, it is so heavy with fuel that the wings scratch the runway and they lose the winglets. And only after they took off, they sent a chase plane to look at what the damage is and to decide whether to go back and to continue, and they decided to continue. And here is the airplane in flight. So look at the kind of flexibility. This, by the way, one of the things that Carlos is dealing with now. And it turns out that these are Dick Rutan and Gina Yeager, the pilots. Dick Rutan is the brother of Burt Rutan, right here, who is this genius designer, now retired, who lived in California in the Mojave Desert and designed crazy airplanes and things like that. Here's our with President Reagan getting the National Civil Medal of Merit for their pioneering. Now I want to talk about Dick Rutan. So Burt was the designer of the airplane. Dick was the pilot. Gina was his girlfriend at the time. This guy, Dick Rutan, was an ex-Vietnam era fighter pilot who had hundreds of sorties over Vietnam, including being shot into the ocean and being saved. This is a pretty brave guy, pretty tough guy. This is a book that I really recommend that you read by them. But he talks about the airplane. Look what he says. He says, we flew at the heavier weights, the flapping became serious. The flights were showing that in exactly 82.5 knots of speed, the flapping of the wings went out of control. The oscillations became divergent. The flattening began to increase in height, doubling with each cycle. Unless the pilot or autopilot stopped it, the wings would literally flap themselves off in about 10 or 12 seconds. If you let go of the stick, this airplane would come apart. They had a body freedom flutter problem. They didn't tell anybody. And since he was such a good pilot, and since the frequency was low, he solved it by basically sitting on the stick and pushing against it. And with time, he realized that if he pushed at 90-degree phase, he could manage to solve it until they burned enough fuel and the airplane changed and the problem disappeared. Because remember, flutter depends on loading, things like that. Look what he says here. Unlike Gina, I hated the airplane and feared it. This is a seasoned fighter pilot. It was the only airplane I had ever been afraid of. I had never gotten used to the flailing wings. I would tell myself that the structures would take the motion, but I wasn't ever really convinced. It was a knowing, grinding fear, and it never went away. And for the first time in my life, I actually felt empathy for those afraid to board airliners. So during the months when we were grounded for the installation of the new engines, I pursued a thorough course of therapy to conquer this fear. So remember the statement from Manchester about the terrifying effect that Flutter had on the pilots of these Handley pages? Here is Dick Rutan. Basically, he says that they never told anybody because they were afraid that the program would stop. And he managed, so this is a first case of active flutter suppression, basically, by a human pilot sitting on the stick and figuring out how to do it until the airplane is light enough and the dynamic is changed. Now, you think this is going to be certified by the FAA? I don't think so. This is another case of an F-18. The F-18 had a serious anti-symmetric oscillation problem. It was a flutter problem. They knew that if they named it correctly, they would suffer grave consequences. So they said it's not flutter, it's an oscillation problem. And they managed to solve it by luck. Their control system had a gyro here. The gyro sensed the rolling motion well enough so that they can feed some signal to the flaps in order to suppress this. How do I know about it? I was Israeli Air Force at the time. There was a possibility that Israel would buy F-18, so we sent 2 of test pilots. These are very seasoned pilots who worked with me on Flutter testing where airplanes shook like crazy. They were brave guys. They came back from St. Louis really shaken, telling me, Eli, my God, this F-18 is shaking like hell. What is going on with the airplane? They wouldn't call it flutter. They called it active oscillation suppression. And later I found out from my connections that it was somebody forgot they engaged the system for the test flight of these. So this is active flutter suppression as solving problems. But my vision has always been that this is a technology that if you harness it from the start, if you use it from the beginning of the design process and make it part of your design process, can revolutionize the way airplanes are done because it's going to save a lot of weight. So this is actually a figure that mostly is taken from my own PhD, except that I replaced a kind of a fighter airplane with a more civil airplane, because I like to work on civil airplanes more than I like to work about. But it argues that if you at the beginning of the design, if you can optimize the structure, the aerodynamics, the control system simultaneously, then you can save an enormous amount of weight. And so here is actually from my PhD. You can see a drone, like this was a drone that NASA built in the 80s to look at active flutter suppression. I showed you in the video how they lost it to Flutter. Remember, this was the first case where the wing, like, bzzzt, and it's gone. So they lost it. But I created a mathematical model, and then I ran some optimization. Here is the weight of the skin when I only play with structural design variables subject to gauge and stress constraints, gauge, strain, and drag constraints, and then I have gauge, stress, strength, drag, and flutter constraints. You see the enormous penalty in weight that you need in order to stiffen the wing enough for flutter. And then you add control variables. And the active system allows you to take most of the weight out. And when you add aerodynamic desirables, you basically go back to a structure as if there is no flutter problem at all. So today on an airplane, you already have a number of active control systems in action. You will have in the center what we call maneuver load control system. In response to maneuvering, measuring G, measuring acceleration, the flap will come in and out in order to distribute the load properly on the wing in order to reduce stresses and save weight. You will have a fast system that would respond to gusts in order to reduce dynamic stresses due to gusts. And so this is now available on all flying airplanes, and it is certified because these systems are for stable airplanes. So they deal with just minimizing dynamic stresses. And you have what we call ride comfort, which is an active system that will reduce the shaking so that passengers or pilots, this is on a B-1 bomber. This is a strategic bomber, supersonic bomber that changed mission. From the time it was designed, the mission changed. The Russians, this was a bomber that was supposed to carry nuclear weapons and hit the enemies, Russia, China, whatever. By the time that it was developed, they had such good systems, ground-to-air systems, that this mission became impossible. And the mission was changed for the airplanes basically flying at treetops, flying very, very low to penetrate. Guess what? When you fly long distances at treetops and you have to go over mountains, the shaking of the airplane because of gusts and winds was so hard that the pilots couldn't take it. Pilots just couldn't function anymore. So they had to add these little two canards here, and they are actively controlled. So they measure the vibrations and they shake. So you already have some forms of active control system, but even with the technology today, problems can happen. So this is the Boeing 787-9. Here is an article from Aviation Week about how they learned from the 787-9 to help with the 787-10. And look what they are saying. An unexpected interaction happened. But what happened, I'll tell you what happened. They designed the maneuver load system to respond to acceleration of maneuvers, which is slow. But they forgot that the accelerometers will also respond to fast oscillation. So that system began to deflect the spoilers in a way that shook the airplane so severely that they have to stop, go back, and redesign the control system. Message here is when you have a number of control systems on the airplane, here we are. We have a system that helps with the rigid body motion of the airplane, what we call handling qualities. We have a system that controls maneuver loads. We have a system that controls gust loads. We have a system that controls ride comfort. Now we have a system, we want to add a system control flutter. All these systems have to work in harmony. You cannot neglect the possibility of bad interaction between them. So you have to show that all these systems have to work in harmony. Here are some cases where flutter suppression was demonstrated on real airplane. This is the NASA drones for aeroelastic and structural design program in the 70s. This is an amazing piece of work by Boeing Wichita with funding from the Air Force. They took a B-52, they modified it by adding control surfaces and by reducing its flutter speed. This carries some external fuel tanks on the wing, so they added ballast weights to artificially and deliberately reduce the flutter speed of the airplane. And then they used active controls, and they flew the airplane beyond its flutter speed, demonstrating that the active control system could do it. This is the Germans, MBB, together with the US Air Force on an F-4. So here is the B-52, and you can see they used outboard ailerons. They have new ailerons. The airplane is heavily instrumented. They add the ballast weights. And they have these 5 systems working together in harmony. The ride comfort system, the flutter mode control system, the maneuver load control system, the stability augmentation system, and what they call fatigue reduction, which is very similar to. This was done in the early 70s. More recently, Boeing had serious problems with the 747-8. So the 747-8 is the new 747 derivative. The airplane would get into a limit cycle. They started with a cargo version, and then it was followed by a passenger version. Boeing is struggling, like Airbus with the A380. There is a struggle with these large airplanes. There isn't a lot of market for them. It's a beautiful airplane, and at some speed, some altitude, the airplane encountered what they called limit cycle oscillation. The airplane begins to shake, and they couldn't solve the problem. Just couldn't solve the problem. The only way they could solve the problem is through active control. He got into an argument with the FAA. Now, how do I know all this, by the way? Boeing doesn't talk about it. I have a lot of connections at Boeing. I have many of my students at Boeing. I know a lot of the managers at Boeing. This is a serious issue, very sensitive. All I know is from what was published in the newspapers. So what was published in the newspapers, what was published by the FAA, was enough to tell me what was happening. I think I know in quite confidence what really happened. I think that Boeing, this is going to be taped, God forbid. There can be an argument here. I mean, Boeing, my colleagues Boeing is going to kill me. But again, everything I'm saying to you is in the open literature. Is it a limit? Remember, I talked about the difference between limit cycle oscillations and divergent oscillation. So a customer that has a limit cycle oscillation problem can argue with the FAA that it's not a flutter problem. So you are not allowing active flutter suppression yet, but it's not a flutter problem. Like McDonnell Douglas with the F-18, we are solving an oscillation problem. But people at the FAA would say, remember the definition of the British, what flutter is? It's a dynamic interaction, self-sustaining, of structures and aerodynamics. We don't care if it's diverging or if it's limit cycle. This is flutter, and we are not allowing flutter systems yet, because we still don't have confidence in the reliability and the accuracy and all the things that you need to cover. By the way, you are in good hands in the sense that the FAA is very conservative. They would not allow any technology before they're very safe about it. But Boeing being Boeing and being a great company, and the people there are really extremely, extremely capable, they reached an agreement, and the FAA gave Boeing what's called a special condition that allows them to use a system because they were convinced that indeed, with the active system, the vibration is suppressed, but even if you lose, nothing severe will going to go to happen to the airplane. The airplane may be shaking a little bit, pilots will be able to slow down, so no safety, no problem. And then the story repeated itself on the 7847-8 passengers. This is the 787-10. It's a new version, just began to fly a month or 2 months ago, where they lengthened the fuselage. And I read the newspapers, and I look at the FAA publications. So anytime the FAA wants to publish a special condition, they advertise it to the public and they wait for comments before they do this. So I follow this. So even without me everybody telling me, I get an idea of what's happening. So it turns out, and that Boeing, doing flutter analysis of the 787, could not match the 3% damping. Remember I showed you the requirement was that up to design dive speed, you have to show that you have at least 3% damping? They can't. They have one mode where they can only get 1.5. So with a special condition, the FAA allowed Boeing to use an active control system, which is an active flutter suppression system on the 787, but it's on a stable airplane. So again, even though I'm sure that that system would never fail, it will have all the redundancies, all the reliability. Even if you want to imagine the worst case scenario, you're dealing with a very stable airplane, except that it didn't have the exact level of stability that, that the FAA requires. This is an airplane that was designed specifically for active flutter suppression research by Lockheed Skunk Works for the Air Force, was given to NASA. It's designed deliberately to have body freedom flutter, plus two other mechanisms which involve elastic modes interacting. 2 years ago, they lost one of them in a crash. They have one left. It's now being flight tested. And so what I hear from NASA Armstrong is that they are facing challenges, but they're making progress. Hopefully, they will prevail and not lose this second airplane. Two of them were built. It's a beautiful machine, heavily instrumented. Right now, it's the only machine of this kind that is used in flight series for active flutter suppression, except for an effort at the University of Minnesota, which has a very nice center that deal with it. Some efforts in Europe to do things like this. You have here Carlos Esnick's Exhale. Those of you who don't know about this work, I encourage you to look at this. So what is the challenge? What do we need to do in order to put an active system on an airplane with the confidence that it's going to be okay, so that it will allow us to save all the structural weight? We have to deal with high-order mathematical models, so we have to have good control synthesis techniques that would allow you to work with high-order systems. The systems are all multi-input, multi-output, multi-function. Remember, we have to deal with many, many things, ride comfort, maneuver load, flutter suppression, and so on. The systems are parameter varying. They change. As you change Mach number, as you change altitude, the system is changing. If you eject stores, if you burn fuel. So you have to cover all these cases. There is significant uncertainty in the modeling. So you have to look at all the possible cases, and with some acceptable probability, you have to show that you cover all these cases. The systems may be nonlinear. You have to make sure that the hardware is reliable. And you have to have what's called validation and verification. You have to design the system in a way that will allow outsiders to validate it. You can't come to the FAA with some fancy controller which is built on some beautiful mathematical theory, which ends up in a black box where people don't have feel for it right now. They are very reluctant to accept things like this. So you'll have to show what is your system doing in a way that people would understand. As I said, this is a 50-year or so effort. I'm not talking about technology that has not been known. We've known about this technology for at least 50, if not 55 years. It has not been implemented yet because of the difficulties, because of the lack of experience, because of the fear, that psychological element, the fear of flutter. And nevertheless, in research, I would say from the controls perspective, if there are controls students here, every possible control synthesis technique has been tried on it. Single input, single output, robust control, LQR, LQG, adaptive control, everything that has been, I'm saying it cautiously, again, it's going to be taped, so I should not say things like that. I'll say it anyway. I'm missing. Probably there has been a few control techniques that have not been used, but a lot of control techniques has been used on this. I'm going to show you two examples. This is from the 80s. This is a F-16 with the problem of external stores. Remember, the issue is that every time you change the stores, it's a different system. And you have an adaptive system. You have a system that quickly estimates the structure and then modifies the control law in order to deal with it. They tested this adaptive system over 3.5 weeks, about 6 to 8 hours of testing a day, about 2,500 different variations, and their adaptive controller did the job. Their adaptive controller stabilized the system until it didn't. So I want you to know that in order to certify something like this on an airplane, you need a probability of failure of 10 to the minus 9 to 10 to the minus 12 for anybody to even look seriously at you. So clearly, it's a problem. Here is a YF-17 in the transonic dynamic tunnel. Again, they did crazy things with it. They had an adaptive controller, and I don't want to go now into the details of which adaptive controllers they used. This is old technology. There is much better adaptive control now, much better equipment, faster computers, and so on and so forth. But again, the same story. The system did a fantastic job ejecting missiles, changing Mach numbers, changing dynamic pressures, and so on and so forth, until it didn't do it. So it turns out that if you increase the dynamic pressure too fast, it couldn't do it, and it failed. So, way to go. So I talked already why the increased interest now. Much more technology, much more knowledge. The drive for better vehicles is relentless. Less weight, better fuel efficiency. If you can use active flutter suppression and you can save weight on airplanes, the levels that I showed you from my PhD, even if it was a fraction of this, would make a huge difference. So there's a lot of interest in this capability. But for the FAA, there is one major interest, and that is safety. So the FAA, as a US government agency, of course, is interested in helping the industry to develop technology, but their number one consideration is safety. And so when I say on the road to certification, what do we really need? We need to address the issue of safety and certification. And without this, it would not be accepted. The cases that I described to you, the Boeing cases, are exceptional because if the system fails, nothing is going to happen to the airplane. The airplanes are going to be completely safe. But if you want to build an airplane from the start, depending on an active flutter suppression system, in order to reap these weight benefits, you better make sure that this practically never fail. Not only in the cases of moderate flutter, not only in the cases of mild flutter, but in the cases of violent flutter. Remember what it looks like when flutter is violent and you lose your control system for a minute? It's not going to be nice. It's not going to be pleasant. So we need to establish such levels of accuracy of analysis and testing and such margins of safety that we guarantee that we know what we're doing. We have to have widely accepted math modeling techniques. We have to have design techniques that will ensure us that we cover all possible critical cases. That, you remember the F100? So they did everything right, except they forgot that afterburners would hit the fluid of the servo actuators and it would lose stiffness and they would lose 7 tails. So nothing like this can be allowed to change. We need hardware that would never fail, including the effect of the airplane landing in some third world country with some poorly trained maintenance person messing around with the system. You have to make sure that nobody can do anything that will degrade the system. Validation and verification of control law, transparency, I talked about it. We have to harmonize, we have to look at the safety laws from air elasticity, safety law of controls. Control people have been designing control systems with their own safety margins, like gain margins and phase margins, so we have to harmonize them. We have to discuss what are we going to allow a control system like this to do. Maybe only limit cycle oscillations, maybe only mild and moderate flutter. Maybe we are not going to accept it if it's violent flutter, but we are going to accept it if it is limit cycle oscillation or so on. We have to accumulate operational experience, and we have to make sure that all the active system on the airplane are. So, as Perit said at the beginning, I've been actually working with the FAA on this, and realizing that a lot of work has been done, that the generation of giants has been passing away, that you guys may not know even what has been done. I wrote this paper, and it was published in the Journal of Aircraft. It is free. It was called open access. So I paid a little more money, and each one of you can download it for free from the FAA. So in order to do a search You know what DOI is, the digital object identification. Every publication, every paper has a digital object identification number, DOI. So look for this DOI number. Just do a Google search. Look for DOI 10.2514-1.C034442. Get these papers. Those of you who are interested, download it. In that paper, you will see the history of 50 or 60 years. Paper was a bit wrong. It doesn't have 503 references. It has 703 references. Since we are being taped, I want to correct this little inaccuracy. Download it and enjoy it. It has a lot of stories about Flutter cases, successes and failures. The bibliography is organized in an encyclopedic way, so it's very unusual for journal papers. But you look at the bibliography, before the bibliography, you have, like an encyclopedia, you have a list of topics, like in an index of a book. And so you want to look at, first of all the airplanes. You want to know what was done in active controls on Boeing 787. So you go Boeing B787. What was done on the B-52? So each airplane where active control has been applied is in the index. You want to look at different control techniques. It's in the index. You want to look at different equations of motion. So hopefully it's going to be very useful to you. Feel free to download it and to enjoy it if you have time. The last thing I'm going to end with this is it worth it? And here is the issues that I've already mentioned. A lot of things in the lab and in journal papers look great, including active controls, new materials, piezo this, piezo that, all kinds of tricks, artificial intelligence, genetic algorithms, and I'm saying it with full respect, no disrespect. It's one thing to focus on the idea. It's another thing to certify it. By the time you certify it, you have to do so much work, redundancy of systems, checks. Maybe we go with some active system that reduces the weight of the structure significantly, but by the time you add the weight of the quadruple actuators and the quadruple computers and all the lines and this and that, maybe the weight of the system basically is going to eliminate or cancel the gains of the only things that can answer this question, and you have one of the best groups in the country, is multidisciplinary design optimization. So go and talk to Kim Martins, go talk to Carlos. It's only if you know how to throw everything into the blend in a way that captures the fidelity of the modeling, but using optimization algorithms to look at how to best utilize it, that you can answer this question. I would say that it's not clear yet, even to me, even though I preached for it and I dreamed about it all my professional life, is that by the time we take an active system and we bring it to the level of certification, that the gains in the structure will be worth it. So a lot of research to be done on that. And I think that with this I'm done.